Alright, hi guys, and welcome to a brand new PSP GPU tutorial. This tutorial will be creating an application that loads and draws textured squares with both transparent and opaque textures. This code references all the callbacks and functions set up in previous tutorials, and the source can be found in the description. There's also a pure sceGu implementation, and we will be using GU to GL. For our base application code, it's basically the same as the last time. The only thing that we changed here was that we removed the texture 2D. So disabling texture 2D. So now it should be enabled and we should be able to go ahead and run. If we do run the application, you'll see nothing pops up because we don't actually have a texture loaded or set up. So the first thing first that we're going to do is that we're going to be using a library called STB Image. STB is a public domain sort of open source project where basically they have a bunch of different libraries and single header libraries. So for example, they have STB Image, they also have Vertices and a bunch of other ones that you might need. It's very cool to check out, and it's in the link inside of the tutorial. For this, we'll be using STB Image, and we'll be using STB Image to load up our files. I already have it downloaded here in the STB Image directory of the tutorial, and you'll also need to download it. In order to include it, you'll just have to define STB Image implementation. And you only need to do this for one file, but since we only have one file here, basically it's going to have to be this file. It's basically operating on the same principle as GUGL here. So if we include common STB image, we should have STB working right out of the box. Now, because we're going to be doing texture vertices, what we need to include is actual texture coordinates on our vertices. You may have heard of these before, and they are called UVs, so we will define the floating point U and V. This has to be defined before unsigned integer color, or else it will not work properly. Adding on to our existing data here, we'll just go ahead and match it with the code that we already have. So this will be our winding order. As you can see, 0, 0 coincides with the minimum coordinates here, and then the maximum coordinate here becomes 1.0. Nothing has to change for our indices, and what we'll be adding here is that we will add GL texture 32-bit F as part of our vertex type, because now we have vertices. In order to load the texture, we're going to need a couple of helper functions here. The first one will be a method that helps us actually determine the nearest power of 2 to a size. Now this is important because the PSP's graphics engine requires you to have textures which are power of 2 buffers. So, for example, if you have a 72 by 72 texture, the nearest power of 2 has to be greater than that, obviously, to fit it, so it will be 128. So you'll actually end up having a 128 by 128 buffer. So to determine this, we have an unsigned integer, which is the power of 2, as equals 1, and then while the power of 2 is less than the value, we'll just go ahead and multiply it by 2. To do this in a quick way, we can bit shift it to the left by 1, and that's functionally equivalent to times equals 2. And then we will return the power of 2. The next method we will be defining is a method which will help us copy from a randomly sized buffer to a power of 2 sized buffer. So we can define a function here, copy texture data, and it will have a destination, and it will have a source. We'll also need the power of 2 width, so PW, and then we'll also need the integer for the height and for the width, and then we'll need the one for the height. For unsigned integer y equals 0, y is less than height, and y increases. And then we can do for unsigned integer x equals 0, x is less than the width, and then x increases. And then what we have here is that we're going to have an unsigned integer pointer for destination, so we'll cast it to that. So for indexing, it will go column by column. So X goes across every column, and then Y goes up and down every row. So for this, we'll do X plus Y times the power of 2 width. This is because we're copying to a power of 2 buffer. Similarly, on the other side of this, we'll be using the source. And we'll be using X plus Y times width because this is sized to the width of this buffer. In this function, we'll basically be ignoring all of the outside pixels in the buffer, and we will just be copying the ones that will fit in the top left corner of that buffer. Finally, the next method we have here is swizzle fast. And what this does is it performs an operation known as swizzling. And what that does is it essentially remaps the way that an image in memory looks. Now, what's important to understand about it is that essentially it maps it in a more cache-friendly way. So whenever you have data that you're reading, usually the CPU caches that data, and essentially that data is going to then be read and write to. If it misses the cache, aka called a cache miss, this actually causes the entire cache having to be dumped, and then it has to reload from RAM. Now, if you're doing this multiple times, this adds up very quickly, and it costs a lot of cycles because main RAM, or VRAM, is way slower than your actual CPU or cache RAM. So in this sense, because we're aware of cache, using swizzling can actually help us reduce the amount of cache misses and and increase the amount of cache hits that we have, so that our CPU runs way faster when it comes to drawing. So we will define a block X and a block Y, an integer called J, and then we'll determine the width of the blocks. Width of blocks is equal to the width divided by 16. And the unsigned integer height of the blocks is equal to height divided by 8. I didn't mean to type it this way, I meant to type it that way. There we go. And then unsigned integer source pitch, which is width minus 16 divided by 4. And integer source row, which is width times 8. Constant unsigned char, y source equals to input, and unsigned char pointer, destination, there we go, is equal to the unsigned char, or unsigned, sorry, this should be an unsigned integer. Unsigned integer, and this will be the output. Then we'll do a for block y is equal to 0. Block y is less than the height of blocks. And then block y increment. Then for block, first we'll actually set the unsigned char x source equal to the current y source. Then we'll do for block x equals 0, block x equals 0, block x is less than the width of blocks, and then we increase block x. Finally, here we can then say constant unsigned integer source is equal to unsigned integer pointer x source. Then for j equals 0 and j is less than 8, j plus plus, and we'll be doing pointer to our destination plus plus equals pointer to the source plus plus. We'll do this 4 times for the 4 channels. And then we'll say source has to increment by the source pitch. And then we'll have x source plus equals 16. That way we get to the next block. Then we'll have y source plus equals the source row. That's a lot of confusing code. Essentially what you're doing is that you're separating your texture into blocks and then copying those blocks in a different order. And what this does is that it ends up overall reducing the amount of hash misses that you'll have. It's very hard to explain this code, and I would recommend that if you're interested in how Swizzling works beyond just having to do it, that you go ahead and take a look at some more information on how that works. The overall result of this is that the texture throughput that you'll actually have to the GPU is way, way higher if you have Swizzling enabled. Now that that's done, we can go ahead and actually define what a texture is. So we'll do type defined struct, and we'll call it a texture. And pretty much all it needs is unsigned integer for width and height, unsigned integer for the power to width and the power to height. And then you'll need void pointer for your data. You can technically specify this as whatever format you want. It's just important that you track whatever data that you have allocated. Let's get into the actual method now to go ahead and load a texture. So we can do const character, file name, and then we'll define a constant integer here that we'll be using for VRAM, whether or not your texture is loaded into VRAM. It's very important to decide what you do and do not want it in VRAM. For example, if you have like a texture atlas that determines like how a lot of your geometry draws, then you'll probably want to put that in VRAM, whereas maybe like a UI texture that you're not using as frequently, you should put it probably in the system RAM. So to actually load the texture data, we'll do int width, height, and number of channels. And then we'll also set STB set flip vertically on load. And what this does is that it flips over your texture. Some texture file formats will need this flip to occur, and some will not. This all depends on what assets you're using. In fact, we could actually add a constant integer called flip to the arguments here, and have a flip be the argument here. Next part is actually going to be loading the texture, which is actually simpler than you think. We do unsigned char pointer data, so this will be the data that we'll get from the actual texture, and it will be STBI load. We'll load the file. We need to provide the width and the height. So this will actually write to these variables. That's why we didn't initialize them. And when it writes to the variables, it will initialize them to whatever the value it finds is. And the number of channels. We'll also request that it is in RGB alpha format, so RGBA. And then if the data fails, this means that basically if we cannot load the file, we return a null pointer, because it would be unsafe to operate on the data otherwise. We can also do texture pointer text equals texture pointer for malloc, and then size of texture. Technically, this can fail, so this can fail. But for now, we won't handle that because it's not going to be a relevant case, at least in this use case, because our RAM is completely unused at this point. It would be good if you're writing a game engine, however, to actually use this. So we're just populating all the members with the data that we need. So the width and the height are set, and the power to width and height are also set. The next thing that we'll do is we'll also do the calculation of the total size, so that of the buffer that we'll need for the actual texture to be stored in. So we can do texture pH times texture pwidth times 4, because there's 4 bytes per pixel. So then we'll create a data buffer here, unsigned integer pointer, there we go, data buffer, and we will set that to be an unsigned integer pointer, and it will be malloc. Or actually, no, sorry, it should be mem-aligned because you can technically pass this as the only thing that you need. So 16 size. It's mem-aligned to the 16 byte, and then sized. Fix me. This could fail as well, so you actually have to check if this allocation fails. So then we'll use the copy texture data to say that the data buffer is the source, the input is the data, and then we'll have the texture PW, and then texture width and texture height. And this will copy all of our data from the initial STB data buffer here, which is only sized by width and height, to our power of 2 width, power of 2 height. So then we can actually get rid of the original data. So we can image STB image free, and then this is the return value from the STB load, so this is data. Technically this just calls free, but depending on the way that your application works, maybe free is its own custom allocator, so just use this method instead. So finally, we'll do unsigned integer pointer. The swizzled pixels is null. So if we're using VRAM, we're going to set swizzled pixels is equal to get static VRAM texture. This will be PW, and this will also have PH. And then we'll have the format, which is PSM888. And that will get our textures from VRAM. Otherwise, we'll do another memo line. And then this will be unsigned integer pointer. I need to copy that to here too. Unsigned integer pointer for both of these. And then this will be 16 size. Once again, fix me. Allocation can fail. Because memo line can fail, but the get static VRAM texture technically doesn't, because it's not really an allocator, it's just a pointer marching mechanism, and that's not necessarily the safest way to do things, but it's also probably the simplest and easiest to understand, rather than creating a dedicated memory allocator. There's a lot to be said about how allocator design works and how you have to manage that stuff. So then we'll run swizzle fast, and we'll have to use unsigned char pointer for our swizzled pixels. That will be the output. Force const unsigned char pointer here for our input data, so this is data buffer. And then we'll use texture p width, and then this width has to be times 4, and texture p height. Now texture data equals swizzled pixels. We can then free the data buffer, which is no longer required, and then what we can do is SEE kernel decache write back and validate all. And what that does is that makes sure that since we just did this really heavy data operation on memory, we want to make sure that that actually gets written back to the main memory, because whenever you use a texture, the GPU actually is going to read that memory. So if it's in system RAM, for example, and you still have a cache on that, it's not going to read the data correctly, and you'll get some really weird looking textures. If you do decide to write back and validate the entire cache, this actually ends up creating basically guaranteeing that you've synchronized all of your textures to the actual main memory, so it actually works. So return texture as well. We'll also need a function now to bind the texture, because now that we can create a texture, we also need to tell the GPU, hey, we got this texture. So we'll have a function called bind texture that takes in the texture pointer that we just created. And if it's not available, obviously you're going to return, because you can't pass in the null pointer. And then we'll run gltext mode. So this is the texture mode. We'll use PSM 8888, because that's our texture format. It's RGB 88. So the maximum number of bitmaps. Bitmaps is its own concept. Right here, we're not going to use it, so we're going to set 0. A2, this is an unknown variable. There are a few of these in the PSP SDK where we just don't know what the variable actually does. So in this case, we're setting it to 0. And then this is for if our texture is swizzled, and this will be true. We'll then also set the texture func. The function here is basically when you have a color applied to your vertex, how does it blend? And the method we'll be using is texture effects modulate, and we'll be using RGBA. So we'll use all the texture channels. So what this actually is equal to is, it's basically equal to output color is equal to the vertex color times the texture color. So this is it's basically multiply. We'll also set up a texture filter, and this is how the textures are read. Basically, if you use linear, for example, that will be using linear filtering, whereas nearest uses nearest neighbor. There's more to read about that as well and how it ends up looking. For the pixel accurate one, we'll use GL nearest. For some textures, it might be better though if you were to use linear. We'll also be using texture wrapping. This will just specify the behavior if your UV value is greater than the 0 to 1 range. So you can either set clamp or repeat. I'll be doing repeat, so that will, so as the name implies, if you have texture coordinates larger, it actually ends up repeating the texture. If you don't, the other result will then be the clamp. And what clamp does is that it will clamp it to the nearest 0 to 1 value. So that will actually end up resulting in this kind of pixel scale effect that looks kind of strange. And then we'll finally do texture image. Texture image actually sets the texture in the GPU. So everything else that we've configured is basically the settings for the texture, and this is the texture itself. So bitmap levels, we don't really have any bitmaps, so we're going to have 0. The width, so this is the power 2 width, text power 2 width. And same thing happens with the height. And we need the texture buffer width. This one is probably poorly explained in the documentation, but it basically is the same as the actual width. And then finally, we'll have the texture data in here. As you've also noticed from this documentation, it's at its current texture map. Textures may reside in main RAM, but it has a huge speed penalty. Swizzle textures to get maximum speed. This is just another reference here that shows us that, yeah, putting the textures in main RAM is pretty slow. So now that we have this available, let's actually load up a texture. So texture pointer text is equal to texture load, or load texture, sorry. And then we'll just be doing container.jpg. And then I won't be flipping it, but I will be using VRAM. Cool. And then before we draw our square, we just do bind texture, and then we'll bind the texture. Now if we make this, you will see you get a bunch of warnings from STB. That's pretty much expected. And as you can see, we have our texture rendered out here. Congratulations, you finally rendered a texture onto the screen. Now, if we wanted to go ahead and do one more thing here, which would be enabling transparent textures. So, for example, the circle texture here is just a cutout version of the same thing here. So, if I were to create a new texture, texture 2, and I'll call this circle.png, and I created, let's see, we'll draw index square here. So we'll copy this and do the same thing here. And we copy texture 2 and have it on the right side. This might not be noticeable with this background color. Let me change it to be white. If we run it here, you can see that there's some really weird artifacting going on with it because it's not recognizing the transparency correctly. So what you actually have to do to enable transparency is you have to enable something called blending. And what blending does is it specifies basically how the GPU decides to interpret alpha values. So there are a bunch of different functions here. The most common function that's actually provided by OpenGL and a bunch of other libraries is color result is equal to the color source times the source factor plus the color destination times the destination factor. And the color destination is what's already existing on the frame buffer, so that will be your background. And the color source itself is going to be the color of the texture that you're rendering onto that. And then this is times its destination factor. So what we can set here is GL blend func. So sceGu actually allows you to choose which function that you use. So you can do add, subtract, you can use minimum, maximum, reverse subtract. There's a bunch of different things that you can do. So for now, we're just going to be using GU add. No need to reinvent the wheel. And then we'll choose the source factor. So the source factor should be actually so the source factor should actually be equal to the alpha that you're using. And then the destination factor has to be the opposite, so it has to be 1 minus the source alpha. And then there's two values here for if you're using a fixed blending mode. We're not doing that, so we're just going to go 0, 0. And then, of course, in order to use blend, we have to enable GL blend. Now, if you take a look at that, you'll see that, hey, the edges were trimmed correctly, and you don't see that weird artifact that you had before, because it actually respects the alpha values that was given. This also helps if you have a texture that will be translucent as well, and that will determine that. When it comes to translucent textures and combining them, the order that you have to combine them is from the reverse of basically how it's rendered. So you want to have your transparent textures rendered from the Z furthest away to the Z nearest if you're going to do the correct blending order. And this will result in the correct look of what you need. And it has to be this way because this function here isn't necessarily going to provide the same output if I have a different destination here, as in the end color is actually different depending on the order in which it's added. So it's a non-associative function. But either way, congratulations, you finally drawn a texture onto the screen, and you can now use your own images. In the next tutorial, we'll be covering matrices and coordinate spaces, and using that to set up a basic 2D camera. Although the same concepts used in the 2D camera can also be used in 3D. Thank you guys for watching, and have a great day.